Hello everyone, I am Ezgi Sangun and I am a fourth-year molecular biology and genetics student at Bilkent University. In this video, I will present my project on how the capacitance of parallel plate capacitors is affected by the distance between the plates, the plate area, and the dielectric material used. Here, you can see the experimental setup. The plates are made of aluminum foil wrapped around styrofoam with dimensions of 20 to 20 cm, 25 to 25 cm, and 30 to 30 cm, corresponding to areas of 400 cm squares, 625 cm squares, and 900 cm squares respectively. The capacitance is measured using a multimeter. I used paper, wood, and styrofoam as the electric materials. I also used some wires and alligator clips to wire the circuit. To investigate these factors, I performed 3 separate experiments and I'll now explain each one in detail. In the first experiment, I investigated how the capacitance changes as the distance between the plates increases. Starting with a distance of 1 cm, I measured the capacitance, then I increased the distance to 2 cm and 3 cm, measuring capacitance by the multimeter at each step. In the second experiment, I kept the distance between the plates constant at 2 cm and changed the plate area to observe its effect on capacitance. I measured plates with areas of 400 cm squares, 625 cm squares, and 900 cm squares one by the multimeter. In the third experiment, I studied the effect of the dielectric constant by inserting different materials between the plates while keeping the plate area and distance constant. I used styrofoam, paper, and wood as dielectric materials with dielectric constants of 1.03, 2.3, and 4.0 respectively. Here is the formula for the theoretical capacitance. Capacitance increases with the dielectric constant and plate area and decreases with the distance between plates. To evaluate the accuracy, I calculated the percentage error using this formula. This formula compares the experimental and theoretical values to assess the precision of the experiment. Now let's take a look at the results from the experiments as summarized in the tables. In the first experiment, where I varied the distance between the plates, the results show that capacitance decreases as the distance increases. For instance, at 1 cm, the capacitance was 0.033 nanofarads, while at 3 cm, it dropped to 0.006 nanofarads. This matches a theoretical prediction that capacitance is inversely proportional to distance. However, a significant error of 50% was observed at distance is 3 cm. In the second experiment, where the plate area was varied, the capacitance increased with larger plate areas. For example, with a plate area of 400 cm squares, the capacitance was 0.018 nanofarads, while for 900 cm squares, it increased to 0.057 nanofarads. This aligns with the theoretical prediction that capacitance is directly proportional to plate area. However, higher errors were observed for larger plates, particularly 42.5% for the largest area. In the third experiment, where I tested different dielectric materials, the results show that capacitance increases with the dielectric constant. For instance, with styrofoam, which is K is 1.03, the capacitance was 0.025 nanofarads, while with wood, which is K is 4, it increased to 0.062 nanofarads. The highest error was observed for styrofoam at 31.6%. Overall, the experiments demonstrated the expected trends in capacitance behavior. Capacitance decreases with distance, increases with plate area, and is enhanced by higher dielectric constants. While some errors were observed possibly due to experimental limitations, material inconsistencies, and the errors done during the experiment, these results align with theoretical predictions, validating the relationships between capacitors and the tested variables. Thank you for watching my project.